Okay. So today's going to be about square roots, evaluating square roots, simplifying square roots. In the end, I don't think it's an overly difficult lesson. But you know what? Just like a lot of what we just did in the last unit on the last test, you know, it kind of comes down to your knowledge of multiplication tables. And when you're dealing with square roots, you're really dealing with squares, right? And squares are multiplication tables, basically. I mean, you just have to know this stuff. And if you don't, get an app on your phone where you can sit there and practice this stuff all day. Because it'll never go away. I mean, so many things, you know, will be harder if you don't know those things. Okay, so I think if we stay on the track that I think we're on, that we will have our quiz, our first quiz, which will be on this stuff today. It'll just be like a separate thing because this kind of is separate, on the 6th. And the next test will be on the 16th for us. And I know we will have a third test in the 9 weeks, and then we're supposed to do a 9-week test, which will probably be next door on the computers. Okay, that'll probably count as a test grade too, in some way. So square roots, right? The square root of a number, of a given number, is the number that when you multiply it times itself, it equals that number. So like which number times itself equals 9? 3. You would say 3 times 3 is 9. So that means 3 is the square root. Which number times itself equals 25? 5. Right, that's what we mean by a square root. Find the number that when you square it, you get what you're looking for, right? The square root of the given number. You know, this is kind of baby steps here, but okay, so we say if 3 squared is 9, then the square root of 9 equals 3. If 5 squared equals 25, then the square root of 25 equals 5. So that symbol, which kind of looks like a divide symbol when you did long division, right? But it's not. You know, what does a divide symbol look like differently than that? Usually we draw a divide to look like more curved like that, you know. This is more of a sharp angle. Boom, boom. And, you know, and it's just called a radical symbol. That's what it's called. And the number that you put inside of the radical symbol is called the radicand. That's a vocabulary word, right? Radicand. And, I mean, the truth is that we don't just take square roots. We also take cube roots, right? In fact, we also take fourth roots. You know, you could put any number in the hook there, and that tells you what root you're looking for. But if you don't see a number there, that means it's a 2. That means you're taking a square root. That's all we're really dealing with today. Although the SOL, eventually we go back to this stuff later in the year, and we end up doing cubed roots and all the different roots. And that number right there, just to let you know, that's called the index. So the index of this is 2. And it's kind of like when you raise something to the first power, you don't write the 1. If you have a leading coefficient of 1, you don't need to write it. Same thing here. Square root is blank. Now, but isn't it true that if I multiply negative 3 times negative 3, I would also get positive 9? Isn't that true? Negative 3 times negative 3 is positive 9. So wouldn't it be fair to say the square root of 9 is negative 3? Yeah. 3. Here? Oh, okay. Right there. well, I'm about to say, maybe this will address it, what we're about to do. The truth is that the square root of a number could be positive or it could be negative, because a negative times a negative is a positive, and a positive times a positive is a positive, so that works. But most of the time, if you are given a square root, you're just looking at it on the page, you assume they mean the positive. The positive square root is called the principal square root, and that's the one we're interested in. Now, you might get, this is the example, and maybe this explains it for Bree a little bit. If there is a sign in front of the radical, then by all means, you're going to use it, right? And so take B first, right? The square root of 49. We know that 7 times 7 is 49, and so is negative 7 times negative 7. But because there's nothing in front here, then we just go with the positive square root, right? 7. On letter C, there's a negative in front. So they're telling you to put the negative. Or in your mind, you could just like leave that negative in front, take the square root of 4, and you would say positive 2, and then stick a negative in front of it. Right? That's why this is actually negative 2, because there was a negative in front. And then a symbol that you may not have seen yet, letter A, is plus or minus. If they use the plus or minus, that's like saying 6 and negative 6. 2 answers. And you say plus or minus 6. Just means 2 answers. So we always think of the square root as a positive, and then we use the appropriate sign. If there's no sign, it's positive. So go ahead, evaluate those 4. And of course, you kind of have to know at least some of the perfect squares. What's the square root of 9? Right, the square root of 9 would be 3, but it has a negative in front, so you say negative 3. The square root of 25. Do you also put plus negative 5? You just put the plus, right? Plus or minus the square root of 64 would be plus or minus 8. And negative square root of 81 would be negative 9. Okay, so unless it's otherwise indicated, assume they mean positive. And? Okay. Now, like I said, if you, it would be nice if you knew your perfect squares. And this is kind of an excessive list, but the next thing we do is kind of estimate, and we'll use this list. It'll help us to do some of the estimating when it's not a perfect square. But some of these, I mean, I would think for sure up to 12 times 12, you should know. I mean, you should just recognize when you see any of those numbers, right, any of these numbers here in your mind, you go, okay, I recognize that as 9 times 9. Right, that is 11 times 11. That is 12 times 12. We should know these by heart. Memorize. Some of the ones that come after, I mean, we use 13 a bit when we're doing Pythagorean theorem, because Pythagorean triple is 5 squared plus 12 squared equals 13 squared, so it's 169. That comes up. 15 squared, 225. I think we see that one come up. That could be a Pythagorean triple too, 9, 12, 15. So yeah, you end up using that a little bit. 20 times 20 shouldn't be too hard, 400. And you go up, these are all the ones less than 1,000. The highest perfect square, which is less than 1,000, is 31 squared is 961. Say, I don't personally recognize all of it. Some of them I did in the calculator, but I got up to there before I checked to make sure I had that one right. And then these 24 squared, that comes up. What is 24? 7 squared plus 24 squared equals 25 squared. So that's Pythagorean triple. So now, using those, if we're asked for a perfect square, which is not, sorry, if we're asked for a square root, which is not a perfect square, then we estimate by putting it in between these numbers. Right? For example, 32. 32 is not in this list, right? What two integers squared is 32 in between? Yeah, in between the 5 and the 6, right? Well, which one is 32 closest to? Is it closest to 6 squared or 5 squared? 6 squared. So you would say, you would estimate, and I'm going to use a little wiggly equal sign because it's not equals, but it's approximately 6. Right, so if you didn't have a way to figure it out exactly, you could estimate 6. That might help you get where you're going. What about the 103? Which two integers is 103 in between squared? Yeah, let's see. 10 squared is 100. 121 is 11 squared. So it's in between the 10 squared and the 11 squared. Which one is it closest to? Probably closest to the 10. So we would estimate that that is 10. How about 40? Okay, you're going to do the next two. Try those two. Estimate them. What'd you say on number 7? Which integers was it in between? 6 and 7, and which one was it closest to? And was it plus or minus? Minus, right? So that's -7. And 350, looking at that list? Yeah, between 350 is in between these two. So between 18 squared and 19 squared, which one does it look closest to? It looks closer to the 19, so we're gonna estimate these. Do you remember doing a lot of estimating in prior classes? Not necessarily this, but other kinds of stuff. Somehow that they feel like that's something that should be taught. To me, it's like if you just get good at doing things exactly, the estimating will come kind of naturally. So now square roots, we already dealt with the different kinds of sets of numbers, right? So far we talked about rational. Real numbers are rational numbers, integers, whole numbers. We know that actually you could go inside of the whole numbers and have natural numbers. But that's not in their chart right there. Okay, square roots that are not the square roots of perfect squares are irrational. They cannot be put into fraction form. Right? The IR in front of rational means not rational. Cannot be put into that form. And that, there are proofs. I could do one, because I think most of you wouldn't want to see this anyways, might be a few. To just prove why, for example, the square root of 2 cannot be put into a fraction form. And there's actually a little bit at the end of these sections here where they're trying to talk about logic and proofs and stuff at the end of these, and doesn't really fit with what we're doing, and I'm not including that part. But in fact, it is kind of what you end up doing here. You do this. You assume that the square root of 2 is a fraction, and then you prove why that leads to a contradiction, which means you go back and say, okay, well then it can't be true. Okay, so irrational numbers are, okay, just a second. I have to open that up again. Like that noise. Okay, so let's see, that is not ours. That one was ours. Right, irrational numbers, square roots that can't be simplified. And then what's the other irrational number that we know? Pi, Remember, as decimals, irrational numbers don't terminate and they don't repeat. And that's what a square root is. So you could add pi to the list. Yeah. Mm-hmm. If they have a repeating pattern, that works. Right. The only decimal that is not a rational number is a decimal that never stops and it never repeats. So now we could categorize these numbers as, are they real? Are they rational, irrational, integer, and whole numbers? These are the three numbers that they're dealing with here. The square root of 24, the square root of 100, and the square root of negative 81. Okay. If it can be simplified, right, then it's not irrational. Now, what is the square root of 100? It's 10. So which number sets does that fall into? That falls into whole, integer, rational, real. All four. Right? Can a number be both rational and irrational? No. So those two columns are always going to be opposite of each other. So what about negative square root of 81? Is that going to be the same as the square root of 100? What's the one set that negative square root of 81 will not be in that the square root of 100 is in? The whole, right? Because it's negative. And integers are negative, but whole numbers are not. And then the square root of 24. Is 24 a perfect square? No. So that'll be irrational. It's still a real number. Remember, rational and irrational together make up the real numbers. So go ahead and try to order. We're going to order these numbers from I'm going to order these numbers from greatest to least. Sorry. How am I going to figure out where to place these? Yeah, we have to do some estimating here. What about 4/3? If I write it as a mixed number, would be 1 1/3. And where would that be? In between which two integers? So it'd be about right there. Right, there's our 4/3. How about the square root of 5 is in between which two perfect squares? 2 squared and 3 squared, right? Which one is it closest to? Is 5 closer to 4 or 9? 4. So it would be close to that. So we're going to say this is approximately. If I say -2, because that's how we just estimate, we know it's a little bit more. It's about right there. And that'll be the negative square root of 5. The square root of 13. Estimate. In between which two numbers is it? 3 and 4. Is it closer to one than the other? Right. 9, 13, 16. Which is it closest to? 13 minus 9 is 4. 16 minus 13 is 3. Closer to the 4. So that would make it about right there. That's our square root of 13. And negative 2.5, okay, that one we know. That would make it right there. And the square root of 9, 3. Okay, so you have to do a little bit of estimating and then you could put them in order. So you try to do the same thing here. First you could say, what are for these 1, 2, 3, 4, 5, 6 numbers, which sets are they in? And then try to put them in order. a good one. Okay. So let's say we already said this part of it, but I wasn't recording at that time. So this was the rational, and this one was irrational, and we said that one was a whole, and this one was, we've already been using I for integer, but now we've got irrational. I'm going to call irrational IR. How's that? IR. And 4.1 rational and irrational. And then we're going to estimate where these things go. Negative 9/2 goes in between which two? Negative 4 and negative 5, right? Negative 9/2 is negative 4.5. So there's your negative 9/2. 5.2, don't need much help on that one. 5.2, 0, 0. Square root of 7. In between which two?
Please pardon the interruption. All DECA students going to the state fair today, please report to the Commons at this time.
In between which two perfect squares do we find? Between 2 and 3 would be the square root of 7. Is it closer to 2 or is it closer to 3? I mean, it's 9 minus 7 is 2, 7 minus 4 is 3. So closer to the 3 squared. So in between 2 and 3, I'll show it just a little bit closer to the 3. All right, square root of 7. And let's see, 4.1 goes here. And then where are we going to put negative square root of 20? In between which two? Yeah, in between negative 4 and negative 5. Is it closer to one than the other? I mean, 4 squared is 16, 5 squared is 25. Is 20 closer to 16 or 25? Probably closer to the 16, right? Which, in this case, because we already got 4.5 on there, it's important, like for ordering here. This one is going to be a little closer to the negative 4 than it is the negative 5, right? That one is negative square root of 20. So which is, if you had to do an inequality symbol in between those two, negative 9/2 is less than negative square root of 20. They're close, but they're not the same thing. Did you get that? Does it? Okay, I heard a noise. Okay, now we can do some evaluating. If we have an expression which includes a square root, we should be able to plug in and evaluate. I think this is the main thing that we didn't get out of this that we should have gotten, at least before we get to our 9-week test. Again, what does it mean to say evaluate? Plug it in. So we need to plug this in here, and it would be even better if we showed that step. Where do you think taking square roots falls in order of operations? I'm going to guess that, if you have a simplifiable square root, you probably do that first. Okay. So this will be negative 3 times, what is the square root of 121? 11 minus 7. Okay, now what's the operation we do next? And what's the question?
In order of operations, wouldn't square roots go with exponents because they're like the opposite?
The truth is that square roots are like exponents. They are. But that's like a little above where we're at right now. You would call the square root of x is x to the 1/2. It is something you could represent with an exponent. So which do we do first out of this? Negative 33 minus 7. How do we put those two together? They're both negative, so you add them up, and what sign will it be? Negative. Negative 40. So you try that. Evaluate when x equals 4. So we all get the part where we plug in, right? That would be the square root of 4 divided by 4. Now the one thing you can't do, which it happens a lot when we deal with this, you can't cancel a number which is inside the radical with a number which is outside the radical. Right? So I can't go 4 divides into 4, that's 1. Okay? The 4 in the denominator is not inside the radical. You have to simplify. The square root of 4 is 2. That's 1/2. Okay, now simplifying square roots that are not perfect squares. Again, if you think of this like a factor tree, that's fine. You could do it that way. I usually don't do it that way. I usually just try to think of the factors of the number in question that are perfect squares. So, for example, 32. 32 is not a perfect square. It doesn't have any factors that are perfect squares. I mean, you can see 16 times 2. Does it have any other factors that are perfect squares? 32? It could have been 4 times 8, right? But you always want the biggest perfect square factor, because that'll get you the most simplification. Right? So if you can split up the number into factors that include one of the perfect squares, then you do it, and you simplify what you can. The square root of 16 is 4. This is 4 root 2.
Could you do it where it's 2 times 16 and then it just flips around, or do you have to do it
Did you flip these two?
Yes, and the 2 is on the outside.
And then the 2 is on the outside? No. If you ask, what if I wrote it like the square root of 2 times the square root of 16? It's still, the square root of 2 can't be simplified, and the square root of 16 can. So it's still root 2, and then you would have times 4, but always we always write the square root last. You know, make the 4 a coefficient, 4 root 2 of a square root, like that. So you can't flip where the 2 and the 4 go. That means something different. You could like switch the order of the radicals. That's commutative property. I think I have one more, and then we're done. Oh, please. So try the square root of 24 while I get this going again. Simplify without turning them into decimals. Find the perfect square factor. What was the factor of 24 that's a perfect square? 4 times 12 times 2. Is 12 a perfect square? Is 2 a perfect square? Got to think of a factor that is a perfect square. Portia. 4 times 6, right? 4 is a perfect square. So we would split it up like this. Whoops. 4 times 6. And then simplify what you can. The square root of 4 is 2. So 2 root 6. In algebra, this class, algebra 2, whatever, you have to recognize these kinds of square roots that have been simplified but not turned into decimals. They're not going to show you things like that. It'll always look like that. So that's the homework. That last bit where you simplify the square, that actually comes from section 11.2. And there's only 4 problems like it. So go ahead and write it down and work on